Hello students, welcome to lecture number 18 of Computer Architecture course. The topic of today's lecture is IO devices and direct memory access DMA. So far in this course, till the last lecture, we have learned quite a bit on the different memory architectures, starting from direct mapped caches, set associative caches, fully associative caches, virtual memory, ROM, and the different types of DRAM architectures, whether it's SDR DRAM or DDR DRAMs. We've also learned about the ROM architecture, that uses different types of addressing line features and so on, and we've covered about the 4 different classes of memory architectures, including RAM, that includes DRAM, SRAM. Then you have ROM, then you have cache memory, that includes 3 different classes of cache memory: direct mapped, set associative, fully associative, and then you've also covered about the virtual memory and also translation look aside buffer. So all these different types of memory you have already learnt about. Today what we're going to look at is how an IO device interacts with the processor and what is the role of DMA. What is DMA and what is the role of DMA in this particular process? So let's get started. So summary of a computer system: you have a processor that comprises of a control path and the data path. So when we refer to the processor, we are basically talking about the MIPS architecture. You have a memory, which is usually the RAM that we are referring to, and that could also mean external memory or permanent storage. Then you have the devices. These devices are the peripheral devices that are connected with the memory and the processor, or they are usually interacting with the memory and processor, and these devices could be output based or input based, or they could be storage based. We look at the different types of devices, IO devices, and their examples today. So for an IO system, the key parameters are dependability and cost. These are the 2 most important parameters for an IO system. On the contrary, for processors and memory, the key parameters are performance and cost. We really don't focus too much on the dependability aspect, but focus more on the performance aspect. The third is IO systems must also plan for expandability, storage capacity, and diversity, which processors do not care about. In case of processors, we do not focus on expandability property and diversity, which we do care about for IO systems. For IO systems, sometimes access latency and throughput play a secondary role, because as I've just said, the most important parameters dependability and cost, or expandability and diversity, not as much as access latency and throughput. The performance aspect depends on the device characteristics, what type of device it is, the connection between IO device and the rest of the system, how they are connected with each other, and the memory hierarchy and the operating system. That is also very important. So these all collectively play a role in deciding the performance of an IO device. And all the components, IO devices, processors, system software, operating system, everything, they affect the expandability, dependability, and the performance aspect of the entire computer system. So you have an IO device that's playing a major role. We have the processor that's playing a major role. System software, which is usually what we are referring to as the operating system. In fact, compilers also play an important role, and these all collectively, when I'm talking of compilers, I'm also talking of assemblers and interpreters as part of that. So these all collectively affect the expandability aspect, the dependability aspect, and the performance aspect of a computer system. Now let us have a look at the types of IO devices. Based on the following 3 characteristics, the diverse IO devices can be organized as follows. So based on the behavior, it could be input based, which is read once; output based, that is write only, cannot be read; and storage, which can be reread and usually rewritten. We will see some examples of each of these categories in the next slide. Another characteristics is based on the partner. That is, who is the partnering system or a partnering entity with the IO device. So it could either be a human or a machine which is at the other end of the IO device. So this is either for feeding data onto the input or reading the data on the output. Okay, so it just needs a partner. And data rate would also be one of the classifying parameters. The peak rate at which data can be transferred between IO device and the main memory or processor is also one of the classifying parameters of an IO device. So therefore an IO device can be distinguished by whether they serve as an input, output or storage device, and their communication partner as well as their peak communication rate. So these all aspects are the aspects based on which an IO device is classified as. So let's see how a typical collection of IO device when interfaced with a processor, how it looks like. So you have a processor memory, interconnection right on the top in the green box, and the processor is receiving the interrupts from the memory IO interconnect. I'll talk of this interrupts shortly. And this memory IO interconnect is a common bus that is connected with the main memory and the IO controllers, and the IO controllers are there for the IO devices such as flash disk, such as graphic output, such as networks. So each of these have their own IO controllers, and the main memory, they all connect with a common bus which is connected to the processor, and this is the bus that is actually sending the interrupt signals to the processor. And of course we have a cache. The cache is also connected through the bus to the main memory. Okay, so therefore the memory IO interconnect is the interface and between the IO devices and the main processor memory on the top. Okay, now let's have a look at the diverse IO devices that exist. So an IO device, as I said, can be distinguished by whether they serve as an input, output or storage device. For example, a keyboard is a IO device which is classified in terms of its behavior as an input device, and the partnering device is a human. For mouse, the behavior is an input, so it's an input device, and the partnering device is human. The voice input is also an input device, and the partnering device is human. So the reason for having these voice input, mouse, keyboard to act as an input device is that we cannot read anything from here. We can just feed an input, okay, through this input device. We cannot read anything through this. The fourth is sound input. The behavior is input and the partner is a machine, because the sound input can be given without the intervention of human. It could be a sound that is played and that is feeding into the sound input device. Scanner, the behavior is input and the partner is human. Voice output, of course, is output is the behavior of this system. So voice output could be like, for example, a sound system, and the partner is therefore a human. A sound output, definitely it's a output behavior and partner is again a human. Laser printer is output human, because we are printing through the laser printer, so it's an output device. Graphic display is an output partnered with a human. Cable modem, you don't need a human here, so it's both an input output, because it is performing both the modulation and the demodulation of signals. So therefore it's a input output device, and the partnering device is a machine. Network LAN is input output, it's a machine. Optical disc is a storage, magnetic tape is a storage, flash memory is a storage, and magnetic disc is also a storage. So these are all storage behavior based systems, and the partnering device is again a machine. Okay, now let's see how do we give commands to an input output device. To give a command, the processor must be able to address the device and be able to supply one or more command words. Okay, so there are two methods that are used to address the device. The first is memory mapped IO, and the second is special IO instructions. So these are the two methods used to address an output or input device or an IO device. So in case of memory mapped IO, the portion of the address space is assigned to an IO device, and the reads and writes to those specific addresses are interpreted as commands to the IO device. Okay, whenever you do a read or a write to that particular address space, it is interpreted as a command to the IO device, because that address space is reserved or assigned only to the or only for the IO devices. For example, a write operation can be used to send a data to an IO device, where data will be interpreted as a command. Okay, so that's how this works basically for IO device. When a processor places the address and data on the memory bus, the memory system ignores the operation because the address indicates portion of the memory space used for IO devices. So it knows that whenever the processor has placed a particular address and data on the memory bus, the memory system will ignore it, because it knows that this particular operation is meant for the IO devices. Okay, because the address is part of the address space assigned for the IO, okay, and not for the other things. The device controller, however, notices the operation, records the data, and then transmits it to the device as a command. Okay, the device controller will notice the operation, will record the data, and transmit it to the device as a command. The role of a processor is that the processor may have to interrogate the status of the device between individual commands to determine whether the command completed successfully. Okay, so for example, if you have a simple printer, okay, and let's say that the printer has two IO device registers, one for status information and the other for data to be printed, and the status information can have two different types of features. First is a done bit, which is set by the printer when it has printed a character. The done bit will be set to 1. An error bit, which indicates that the printer is jammed or out of paper. In that case, the error bit will be set to 1. So these two bits are specifying the status, okay, of the register. So through the status register. Then you have the data register, where each byte of data to be printed is put into this register, and the processor must wait until the printer sets the done bit before it can place another character into the buffer. Okay, and the processor must also check the error bit to determine if the problem has occurred. In case the error bit is set to 1, that means a problem has occurred and no further character can be placed into the buffer. Okay, and whenever the done bit is set to 1, it means that the next character can now be put into the buffer for the processing of the IO device. So there are specifically two different types or algorithms through which an IO device can communicate with the processor. The first is polling. In polling, what happens is the process of periodically checking the status of an IO device is performed by the processor to determine the need to service the device. Okay, through pooling, what happens is that the processor will periodically check the status of the IO device to see if the respective work is finished, and or if an error bit has occurred or been set to 1, then it will need to service the device in that case. The second is interrupt driven IO. In this case, a scheme is adopted where an interrupt is sent to the processor whenever an IO device needs attention. Okay, whether that is for providing the data onto the data register or whether it is for servicing in case an error has happened. But here the processor will not come automatically and keep checking the status, but rather the processor will only come and check the status when an IO device will send an interrupt signal to the processor. So therefore this is interrupt driven IO. Okay, not like polling, where polling happens at periodic intervals of time by the processor coming and checking the status of the IO device. So in pooling, what happens is it is the simplest way for an IO device to communicate with the processor, and the processor periodically checking the status bit to see if it is time for the next IO operation is called pooling, and the IO device puts the information in the status register, and the processor must come and get the information from there. So whatever the processor has to come and check will only happen through the status register, and whatever operation has to be performed will happen through the data register. So that's how this works. The disadvantage, as obvious, we can understand that first of all, it wastes a lot of processor time because the processors have to come and check at periodic intervals. Therefore the processors will waste a lot of time, and this is also possible because processors are faster than IO devices, and the processor may read the status register many times only to find out that the IO device has not completed a slow IO operation. So that is quite likely to happen, and when a device completes an operation, the processor must read the status register to determine whether it was successful. Okay, so to check if the operation is successfully completed or not, the processor has to read the status register to determine whether it is successful or not. So in order to overcome this slow pooling process, interrupt driven IO is certainly a better alternative. In this case, what happens is the interrupt driven IO attacks the problem of the processor having to wait for a slow device. So instead of waiting, the CPU continues with other tasks and calculations. The device interrupts, that is the IO device interrupts the processor when the data is ready, else the processor will just normally continue its work. The interrupts are external events that require the processor's attention, okay, and the peripherals and other IO devices may need attention, okay, by sending interrupt signals to the processor. These are not really errors, because many people consider them to be like errors. These are not really errors, but these are external signals known as interrupts. And the interrupted program, that means whatever the processor was working on until the interrupt signal came, the interrupted program will need to be resumed after the interrupt is handled and serviced. So how will it again resume back to the interrupted program? Is through the help of an operating system. The OS has some responsibility here. First, it saves the current state, okay. Second, it finds and loads the correct data from the hard disk, and third is it transfers data to and from the from the IO devices rather. So here the OS has a role in case there's an interrupt coming in. So do we have a better option than both pooling and interrupt driven IO? Yes, we have an alternative option, and this option is known as DMA, direct memory access. So both pooling and interrupt driven IO transfers put a lot of burden of moving data and managing the transfers on the processor. They put a lot of burden on the processor, burden of moving data and managing the transfer, both. So how can DMA help? So DMA is a mechanism that provides a device controller with the ability to transfer data directly to the memory and from the memory without involving the processor during the transfer process. Okay, I'm not saying that it does not involve the processor at all. I'm saying that it does not involve the processor during the moving data and managing the transfer process happens. Okay, so it provides the device controller basically. So every IO device has its own specific device controller. So it provides the authority to the device controller to transfer data directly to the memory and from the memory, okay, without involving the processor. So for high bandwidth devices such as hard disk, the transfers primarily consist of large block of data, usually hundreds or thousands bytes of data, and therefore in such a situation where you are transferring a large block of data, if you are involving the processor, it will actually occupy the processor for a long period of time. Whether we are doing through interrupt driven IO or pooling, it actually blocks the processor for a long time. However, with the usage of DMA, the processor can be offloaded from this responsibility and the device controller can transfer directly to and from memory without the processor. Okay, I'm saying not completely without the processor, because I'm going to say where the processor has some role to play in the next slide. But as of now, just keep in mind that the processor has a minimal intervention in this entire process. The device controller uses interrupt mechanism to communicate with the processor, but only on completion of an IO transfer, okay, or when an error occurs, or when you start. Okay, I'm going to speak about that. So three things: when you start, when you complete an IO transfer, and when an error occurs. Then only through an interrupt mechanism the device controller will communicate with the processor, else it will not. The DMA controller becomes the master and directs the read writes between itself and the memory. So that's how this basically works. Okay, now let me have a look at what do we do when you have a DMA transfer. Okay, what are the three major steps for DMA transfer? The the first step is that the processor sets up the DMA controller, which is the device controller, by supplying the following 4 information. The first is the identity of the device. Second is the operation to perform on the device. The third is the memory address, that is the source or destination of the data to be transferred. Okay, that is the source or destination of the data to be transferred. So that is also the information that needs to be supplied to set up the DMA controller. And last is the number of bytes to be transferred. Okay, so these 4 information has to be provided by the processor to set up the DMA controller. The second thing is the DMA controller starts the operation on the device. How? First, the data is available from the device or memory. It transfers the data. The DMA device supplies the memory address for the read-write. If the request requires more than one transfer, the DMA unit generates the next memory address and initiates the next transfer. Using this method, the DMA can transfer thousands of bytes without involving the processor during the management and transfer of the data process. The third step is once the DMA transfer is complete, the controller interrupts the processor, which can then determine by interrogating the DMA device or examining the memory to check if the entire operation of data transfer is complete. Okay. Now let us have a look at an example of a DMA transfer. So let's say we have a ADC peripheral unit. So ADC stands for A to D converter, that produces a new conversion result, let's say every 4 microseconds. Okay, conversion means converting an analog data to its digital counterpart. The CPU has configured a DMA controller to read this new data and store it in RAM memory. So the source address for the transfer is always the ADC data register. That is the source address, because from there we are actually reading it. The destination address is an address in the RAM or the RAM memory. So this destination address is increased by the DMA controller with each consecutive transfer. Okay, that is once the A to D conversion has happened, it will transfer it after a certain periodic interval of time, and the address also will be incremented accordingly. The ADC indicates to the DMA that the new data is available using the dedicated interface. When a DMA detects the new data is available, it proceeds by reading the data register of the ADC. Okay, and this read data is then stored in the DMA FIFO buffer, because internally it has a FIFO buffer where it stores it, and the DMA controller checks that the memory bus is not busy and then transfers the data from the FIFO buffer to the destination address in the RAM. Okay, so this FIFO buffer therefore is an intermediate storage inside the DMA controller. Just in case if the memory bus is occupied or busy, then it will store it intermittently or hold it intermittently, and once we see that the memory bus is not busy, then it will transfer the data from the FIFO buffer to the destination address in the RAM, and accordingly the information will be stored inside the RAM memory. This entire thing therefore concludes a single DMA transfer. That is what I am trying to say. So this shows a pictorial view of the CPU. You have the DMA controller of a respective peripheral unit, and you have the memory. So the master interface is of course the CPU and the DMA controller. So the DMA controller is connected with the peripheral through a handshaking mechanism, and you have a FIFO buffer inside the DMA controller, and they're having a two-way communication through handshaking process. And same, the peripheral unit in the DMA controller has two-way communication through a handshaking process, and the data transfer also happens from the, for example, peripheral unit, which is A to D unit, and it will send the data to the DMA controller, or the DMA controller will read it from the ADC data register and will put it up in the DMA FIFO buffer. And this is the RAM where ultimately the data from the FIFO buffer will be put inside the common bus in the respective destination address of the RAM, and it will get stored here. So every peripheral unit or every IO device will have its own respective DMA controller that handles the transfer of between the IO device and the memory. So summarizing, the DMA transfer is there for a two-step process. First is each DMA controller has its own FIFO buffer, and they are used in case a busy resource is preventing the transfer from completing. So if the resource is busy, if the memory bus is busy due to bandwidth limitation, or it's occupied due to some other operation, then FIFO buffer will intermediately hold the data that it has read from the unit, peripheral unit, and then it will transfer it to the memory bus. So using FIFO therefore allows DMA controller to perform two-step transfer. First is a read access. The data is transferred from the source address to the DMA FIFO. This is the source address of the peripheral unit. Using read access, it will transfer the data from the source address to the DMA FIFO, which is inside this DMA controller. And the write access, where the data is transferred from the DMA FIFO and it is written to the respective destination address of the RAM. The advantages: it improves performance of embedded applications, okay, and second is it reduces power consumption, as involvement of DMA controller reduces the burden on the processor, as the processor involvement is drastically minimized. So therefore the processor can operate in low power mode or sleep mode in case whenever you have an IO operation having being done between an IO device and the RAM or memory. Okay, so we are done with this IO device and DMA thing. So we have learned a lot of concepts on DMA. We have learned concepts on pooling, concepts on interrupt driven IO. You've also learned the different diverse classifications of IO devices, whether it's with respect to behavior, with respect to the partnering mechanism, or with respect to the peak communication rate. So all these three parameters actually classify the IO devices that we are talking about. You've learned about the disadvantages of pooling, you learned about the disadvantages of interrupt driven IO, and you've also learned about how DMA controller plays an important role whenever you have a operation to be done between an IO device and the memory. Okay, thank you, and in the next lecture we are going to focus on multiprocessors. Thank you so much.